Okay, so our next presenter is Richard Lane from the University of Sydney. Does anybody here subscribe to Word of the Day from dictionary.com?
Yeah.
Yeah? Did you guys happen to notice what today's word was? Totally random. Today's word was sidereal. Does anyone know what that means? Richard's laughing. No one else knows what sidereal means? See, this is a learning experience tonight. Sidereal means pertaining to the stars. Is that correct?
It is.
So Richard is going to talk about how the techniques are used for mapping, not just the Earth, not just working with datums and spheroids and whatever, but mapping the sky. So I'd like to invite Richard Lane from University of Sydney and also Sydney Observatory to talk to us about mapping the sky. Thank you, Richard.
Thank you. As Steve said, I'm Richard Lane. I'm a PhD student at the University of Sydney, and I'm going to be talking about mapping the sky. And by the way, as our esteemed Google colleague here has also talking about Movember here, so he's not the only one. There was somebody else here, it wasn't just me. And so basically one of the problems with mapping the sky is we have to map the sky from inside the galaxy of the Milky Way. And you can see the problem with the confusion here of observing near the galactic plane because you have stars behind each other. You can't see individual stars. So what you need to do is either look out of the plane or do something else. Now, the other problem with mapping from inside the Milky Way is you have this thing called extinction, which is a problem with gas and dust. And now the problem with gas and dust is that you can see the optical wavelengths here, that the gas and dust obscures a lot of the light. But if you use longer wavelengths like infrared here, then the longer wavelengths are not absorbed or scattered by the dust as much. And so you get a better picture of the Milky Way from that. Now, this is the entire sky, and believe it or not, this is about 41,000 square degrees of sky. And so the largely important thing when you're mapping large parts of the sky is a large field of view, because otherwise you're using a lot of telescope time. The other thing that's important is the aperture. Bigger is always better, sorry guys. This here is an image so you can see there's a 5 times improvement here in aperture, and you can see that's a marked difference in the resolution. Now, in a similar kind of way, this is the Subaru telescope and the INT telescope, and if you're using the INT telescope to do this survey that we did, it would take a 7-night observing run into a 77-night observing run, 11 times longer, which is obviously kind of prohibitive. Now, okay, I've gone back now. Bigger is not always better, sorry. Because here you have a series of different apertures, the largest optical telescope in the world on the other side. The problem with the larger optical telescope is that the field of view is usually very small unless you use some kind of optical trickery, and this is what this 2DF instrument has done. Now the 2DF instrument, it was commissioned and built by Australians in Australia, the first instrument of its type in the world, built in 1994, and it uses a very complex piece of optical instrumentation, and you can see here there's a whole lot of corrector plates at very specific distances from the focal plane to give you this full 2 square degrees field of view for a 4-metre diameter aperture. Now, I've forgotten what the next slide is, so I'll just wait for a second. Oh yeah, of course. So optical advances like this have allowed things like large-scale surveys to be done. And this first one of these is this DSS, the Digitised Sky Survey, although this was never actually intended originally to be an all-sky survey, but that's what eventually happened. These are the 2 telescopes here. Obviously, they worked through the 70s. And this was done from 52 years of optical information from these 2 telescopes on opposite sides of the globe to cover the entire sky, digitised, and produce the first ever all-sky map. Now this here is a 2-micron sky survey, an infrared sky survey done in 1969, and here you can see the galactic plane just here, and this identified 5,500 infrared sources, but since then, 100 million-fold improvement in optical technology has meant that in 4 years, the 2-micron all-sky survey was able to identify 500 million stars and 3 million galaxies. All the galaxies here are coloured by redshift, and you can ask me about redshift at the bar later. Now, this is the Sloan Digital Sky Survey, which is supposed to be finished in 2014, and this is producing a map of a quarter of the sky in the Northern Hemisphere, and you can see there are about 3 million galaxies, a million galaxies and 100,000 quasars so far identified here. SkyMapper, with the original name that it has, was being installed in September of this year into Siding Spring Observatory in northern New South Wales. This is going to take over from SDSS in the southern hemisphere. Okay, the problem with these survey telescopes, though, is that they have very small apertures, so they can't go very deep into the universe. You can see the distance cut-offs in these surveys is basically due to the aperture and time constraints. So having a larger aperture is a very important thing, And so this is the newest pieces of technology coming up in the next 3 slides. The Giant Magellan Telescope. Each of these 7 mirrors here is an 8.2 metre diameter, and you can see the first of the blank mirrors being produced over there. This is as far as the technology has gone so far. The next telescope, the European Extremely Large Telescope. I'm not kidding, that's what it's really called. This will be as high as the Eiffel Tower with a 42 metre diameter mirror. It's going to cost about €1 billion to produce this thing, and it should be built by 2018. But this next telescope is my favourite. You won't believe what this stands for. It's the Overwhelmingly Large Telescope. It has a 100 metre diameter aperture, and if the budgetary constraints of about €2 billion so far, it means that they have to cut back the size of the aperture. It's going to be called the Originally Was Larger Telescope, and I'm not kidding about that either. Anyway, so unfortunately though, when you do go observing and trying to map the night sky, one of the things you do have to do is, well, you're always in the hands of the weather gods, so unfortunately that does happen sometimes. But thank you very much.